Hello everyone, I'm Mr. Bailegi Tayi, your instructor introduction to distribute systems. So far, we have discussed about Module 2, Chapter 1, about models of distributed computing. Now, today, we will discuss about Module 2, Unit 2, Client-Centric Consistency Model. Okay, so let's go. Let's start from objectives. By the end of this unit, you will be able to 1. Define eventual consistency and its role in distributed data stores. And the second objective here is contrast monotonic reads with read your writes consistency models. And the third objective here is illustrate a scenario where monotonic writes prevents write conflicts for a client. And the fourth objective here is differentiate between writes follow reads and monotonic reads regarding causal relationships. And the fifth objective here is determine which client-centric model best ensures a user always sees their own updates across various replicas. And the last objective here is formulate a client-centric consistency guarantee that combines read writes and monotonic reads. Those are the objectives that we will focus in this chapter, which is called client-centric consistency models. The first one is introduction to consistency models. In distributed systems, consistency refers to how data is synchronized and shared across multiple nodes or processes. A consistency model defines the rules and guarantees about how operations on a shared data appear to different clients, ensuring that clients' views of data are coherent and predictable. As you know, different systems and use cases require different consistency models based on performance, availability, and fault tolerance thresholds. So, consistency models determine how updates to shared data are propagated and when and how a read operation reflects these updates. So, client-centric consistency models focus on the consistency of the data from the perspective of individual clients or processes, ensuring that clients observe data in predictable way. So, client-centric consistency models are generally used for applications that lack simultaneous updates. That means most operations involve reading data. Only few processes involve in updates. It concentrates on what specific clients want instead of what should be maintained by servers. Let's try to discuss about some common client-centric consistency models. The first client-centric consistency model is eventual consistency, and the second one is monotonic reads. The third one is monotonic writes, and the fourth one is read your writes, and the fifth one, and the last one is writes follow reads. Those models are often designed to provide a balance between availability and latency in distributed systems, particularly when full synchronization. That means strong consistency is too costly or it is most of the time impractical. The first client-centric consistency models, as I told you earlier, eventual consistency. So, in many cases, concurrency appears only in restricted form. In many applications, most processes only read data. In some cases, if for a long time no update takes place, all replicas gradually and eventually become consistent. This situation is known as eventual consistency. Client accesses distributed data store using generally the local copy. So updates are eventually propagated to other copies or other replicas. So eventual consistency essentially requires only that updates are guaranteed to propagate to all replicas or copies. However, problems arise when different replicas or copies are accessed over a short period of time. For example, for the mobile user exam, eventual consistency data stores will not work properly. As you observe from this image, some replicas need to maintain client-centric consistencies because clients uh, moves to other location or transparently connects to other replicas for the purpose of updates or for the purpose of consistencies. But this situation may not work in the most times. A mobile user accessing different replicas of a distributed database has problems with eventual consistency. Note, under eventual consistency, if no new updates are made to a data item, all replicas will eventually become consistent. However, if updates continue, there may be temporary inconsistencies between replicas. The second client-centric consistency model is monotonic reads. Monotonic reads ensure that if a process reads the value of a data item x at time t, any subsequent reads of x will always return that same value, or it should be the most recent one. Okay, so it guarantees that a process will never see an older version of x after reading it. For example, consider a distributed email system where a user mailbox is replicated across multiple machines. If a user reads their mail in San Francisco and later accesses it from New York, monotonic read consistency ensures that the message seen in San Francisco will also be available when they open their mailbox in New York, even if updates are propagated lazily across the system. So here, see these images A and B. Okay, the read operations are performed by a single process P at two different local copies, that is L1 and L2 of, but they have the same data store. Okay, here as you see, there is local copies of L1 and L2 from the two pictures A and B pictures. The same thing L1 and L2 in the same, but orders are different. As a result, uh, the monotonic read consistency on A is correct, but the monotonic read on B is false. See the notation here. The set operation mean the set right of xi at time t is the set of right operations at local copy I or li that lead to the version xi of x at time t. That means the set rights of xi at T1, comma, the xj at T2 indicate that it is known that the set right xi T1 is the part of the set right at xj T2. Okay, so as you observe from the picture, there is no parameter t, it is omitted, but this is expressed in this way. So to guarantee monotonic read consistency, all operation in set right xi should have been propagated to the local copy of L2, okay, before the second read operation takes place. In other words, we need to know for sure that the set right x1 is the part of the set right x2, which is expressed as the set right x1 semicolon x2. That means ws in the parenthesis x1 semicolon x2. Okay, uh, we can read or express this is the set right of x1 semicolon x2. That means the set right of x1 is the part of the set right of x2. Okay, so this is how we try to express. As a result, as you observe from the images, there is some order are omitted from the picture B. So it is not that much